he has to remove the thing, and the doctor use it to treat the patients. Okay, you hear it, please. Thank you.
Thank you. You steal my joke now. Okay. Okay, I'm Narong Lit Jor Ho. I'm from School of Physics, Institute of Science, Suranari University of Technology, SUT. And today I'm gonna talk about a project that we are trying to develop in SUT and also the Proton Center at KCMH in the topic of the development of the proton computer tomography or the PCT prototype. Well, in this project, we are not only work in this SUT and KCMH, but we also have some collaboration from Bergen University of Norway and also CERN. Well, first of all, I will tell you what is the PCT. PCT is another type of medical imaging instead of X-ray CT. There are some benefit of the PCT over the X-ray CT scan. Well, as you have already learned from Martin and also Dr. Chakapong in the first two talks, this is the proton therapy. I mean, then today I think you heard about from the developer of the accelerator and doctor, and then today I talk about the user. I mean, okay, it based on my experience. My father has cancer, also brain cancer. I just want to say that in the beginning, how you know that you has cancer. My father start from he cannot say the thing correctly. He called remote control as a sister. He called sister as a remote control. He cannot count the number correctly. And then he kind of missed memory. And then we sent him to the hospital. The doctor do CT scan, that is X-ray CT scan, and immediately found 2 tumors in his head. And then immediately the doctor said, okay, we have to do a brain operation. I don't know, for me, he just need to open the skull and then take the tumor out and then close it. He took like several months to be recovered. Because at that time, that is 8 years ago, at that time we have no proton therapy. And after that, there also it was found that the brain tumor that come from lung cancer. And then he still have to do chemotherapy and then the radiotherapy because it was spread out already. And then also some spot inside his head also. And then I think, okay, this is the disadvantage of the operation and also chemotherapy and also radiotherapy, right? Well, then the proton therapy take an advantage because you no need to open your skull, you know? I mean, then you just shoot the proton inside the patient head and then, okay, let proton deposit energy here. And then another advantage is that the proton deliver lower dose to a normal tissue and higher dose to directly to the tumor tissue. And then now, luckily, it is available at KCMH now. Well, there are also some disadvantage of the proton therapy because it has a high operating cost. You need an accelerator, you need technicians around to run the accelerator, and then you need a large space for the facilities compared to the radiotherapy or chemotherapy. Well, but what is the problems here? As you can see from the picture of Dr. Chakapong in this morning, when the doctor prepared to do the proton therapy, they has to do the treatment plan. What is treatment plan is he has to draw a picture of the proton, that which direction the proton shooting go, how many doses that the proton have to deposit here. But the image that come from the diagnostic part is the image from X-ray CT, right? I mean, let's imagine that what is X-ray CT? X-ray CT is the black-white gradient picture, right? Or 3D modeling. This means that picture tell you how much your organs or your tissue absorb the X-ray, but not how much the proton will deposit inside that tissue, right? But won't it be better if we can construct a picture or an image of a patient body with the proton that tell that which kind of organ, how many doses of the proton will deposit the energy into that organ directly, and that will be better. And for sure, there are already some calculation, a lot of publication revealed that, okay, PCT or the proton CT scan would be slightly better stopping power compared to the normal CT. This means X-ray CT is not really 100% compatible with the proton therapy. If you have the proton CT, is more compatible with more compatible with the proton therapy with lower the uncertainty in this case. This is the first reason of good things of the proton CT scan. The second thing is, when you do the X-ray CT, the doctor cannot repeat the X-ray CT that often, because the patient will accumulate higher dose, right? More than limit. This means the doctor have to wait for a while and then do again the CT scan. And we expect that the proton CT would deliver a lower dose compared to the X-ray CT, because the proton CT, you just shoot the proton throughout your body and then didn't have a black peak in your body for the proton CT. And then compared to the X-ray CT, it can be lower dose compared to the X-ray CT. And this means that we can do more often proton CT compared to the X-ray CT, and that would be good for the treatment for the doctor. And the last thing is, another thing is, sometimes, I don't know, I'm not sure, X-ray CT, you need the contrast media, no? You have to inject the contrast media to do this, and then it's not good for your kidneys. But the proton CT is not really require this. The next thing is, for the X-ray CT, when the doctor asks you to do the X-ray CT, then you have to do it today, and then for the next week or someday you will do the proton therapy. This means there are some times in between, right? But if you have the proton CT, you can just do it 5 minutes before the treatment. I mean, maybe exaggerate, but okay, won't it be better if because we use the same machine, right? We use the proton beam. This means it's also possible that we can have an integrated system. You imagine your patient body just, I don't know, some minute, some hour just before the proton therapy start, right? This would be good. I mean, at least there is no less chance that tumors or cells that move or the patient body change, location of the cancer change. I don't know, but okay. Then the three main important thing is, first is the proton CT should give a slightly better the proton stopping power map for the proton therapy. Second is maybe the patient accumulate lower dose, and the last one is you can have an integrated system for the proton therapy. Well, and I summarize into this picture. You can see, proton therapy is better in the stopping power, lower dose accumulation, don't require the contrast media, integrated system. But the disadvantage of the proton CT is that the scanning time. Nowadays, when you go to the X-ray CT, you just move the X-ray source, no, in the circle. But it will faster than you have to move the gantry, right? Then proton CT should give a higher scanning time. And the next thing is the operating cost. You pay more when you move a gantry compared to moving the X-ray source, right? Well, then come to what should proton CT look like? What is the component of the proton CT? First thing, what you need is, of course, the proton beam, where we luckily have at KCMH. The next thing is, you probably need a tracker. We should track the incoming proton coming out, and then a phantom as the representative of the patient, and then another tracker to track the particle, the proton, after scattering from the phantom. The next thing is you need calorimeter to measure the residual energy of the proton after passing through this, and then the DAQ system. And this is our latest prototype of the PCT that we are currently developing. You can see that, okay, we have a proton. Actually, okay, I didn't move the gantry here. I mean, gantry should be here, and then proton come from the right to the left, and then here is the acrylic. We are going to use as the phantom. It is a 1/4 of the cylinder acrylic, and then these are our range sampling calorimeter that I will talk about this later. And you can see this part is the motion part, which I can be able to move the phantom in 3 dimension and also rotating stage here. We can do like 3 dimension plus rotation part automatically. Well, to access the proton therapy, actually this project is not started by me, but Ajahn Chinorat start. And then to access the proton therapy in 2017, we means SUT, CMU, SLRI, and KCMH signed MOU with the GSI, and then we are able to access the Proton Center at KCMH and also biological laboratory at CU, at Chulalongkorn University also. And well, from the customer part, the Proton Center in Thailand, it starts from 2020, actually 21. The first, it's delay actually. It probably should be 2020, but okay, 1 year delay, I think. And then the energy of the proton is 70 to 220 MeV. Actually, this energy is slightly lower than the proton CT because if you want to shoot proton from one side of your body to another side, you need around 250 or more MeV. But okay, we have to do what we have. Then I think maybe hand CT scan or head or some small animals, we can probably do the proton CT in the near future. And then the pencil beam with 5 to 7 millimeter, 1 sigma Gaussian beam. It depends on the energy. When the energy is low, 70 MeV, the beam is bigger, 7 millimeter. And when the energy is high, 220 is 5 millimeter. And we are able to operate in 2 modes, that is Partian mode and QA mode, which are able to access some signal. And moreover, we also signed the non-disclosure agreement with the variants, where we have to get, where we are able to get to know some electronic parts of the variants when we would like to get a signal of the proton beam. Well, let's go to the principle of the PCT. How can we get an image from this? Well, first, if a proton comes to a matter, what you have is the inelastic scattering, multiple Coulomb scattering from the nuclei. And then with this, what happens is proton will lose energy inside this sample, and will also deflect from the original direction. This means you have the proton come and then deflect and then deposit some energy. What we have to do here is we're gonna have to track the proton before and after passing through a phantom, and also measure the energy that after passing through the phantom also. Well, because the multiple Coulomb scattering, the principle to do the image reconstruction is not like X-ray, right? X-ray, you just export the X-ray and then let's see that how much you have an X-ray left. You have a black-white picture because some organ absorb the X-ray. But here you have to get an information from the energy that really deposit, which should be related to the electron density of the phantom of the organs. And also for the spatial, you probably need to know the angle that really the proton really deflect. But of course, due to the multiple Coulomb scattering, you probably need a clever algorithm to track the proton that really see what is the dimension, or you probably need a higher statistic to really track the proton. Then, as I told here, the requirement is more than 250, more than 220 that we already have. One probably think about the booster of the Proton Center at KCMH that we also trying to think, but also, of course not easy. That to boost the energy higher than 220, and then we are able to penetrate the adult tongue. And then trunk. Okay, and then here is some better Bosch formula, and then finally, if you know the energy in and energy out, and then we are able to get the E here, I think we'll get the electron density from this image. We hope we can do image reconstruction. Now the question is, how can we track the particle? How can we measure the energy? Then thanks to another collaboration with CERN, Ajahn Chinorat also have collaboration with CERN. He part of the ALICE experiment in the past we are developing the innermost tracking system we call the ITS or innermost tracking system part. This part of the detector consists of an array of a sensor. This sensor named Alpine sensor. It is a large ion that is ALICE. The Alpine sensor is the silicon-based monolithic active pixel sensor, which is the part of the ITS here. I should go to this. It is the CMOS sensor, which we are able to measure any charged particle that coming through here. And it has a very, very powerful sensor because it has low power consumption. Low budget material means the sensor is very thin, only 50 microns. And also it has very high resolution. You can see the size of the sensor. Here is only, for example, this sample is 3 centimeter times 1.5 centimeter. And then there is 1024 times 512 pixels here. The pixel size is 28 times 28 micron. Well, with this, it also have high efficiency, 99%, and then a small fake hit, this one. Well, this sensor was think to be a prototype, part of the prototype of the PCT to track a particle. But the small sensor have to be put in an array to become a larger sensor. This idea was developed by the backend PCT development teams where we also collaborating with. This is the model, and this is the one that they are developing. This guy is the Professor Dieter from University of Bergen, and this is me. And then we visit them. But luckily, the sensor is we still don't have a sensor because the sensor is super difficult to produce, and it was produced in Ukraine. And then there's some trouble with the sensor that we are not really able to get the sensor, I mean, it's only once in the world that the sensor was characterized, was produced. This means this group, the backend group also was delayed, their project was delayed also. Yeah. Okay, but we also discussed with them, and then we're trying to test a smaller prototype to use a smaller sensor. Here is this is the sensor area that becomes our calorimeter, where we're going to put 2 of the Alpine sensor in this area. But again, luckily we don't have a sensor. Then this model we have, and then we buy everything except sensor. And then we are not finishing yet the sensor. And then I come back and think again what we can do with our existing sensor in our laboratory. We have only one Alpine sensor here. And then we think we think another way. Instead of we shooting proton beam, I mean, here they're going to shoot can be a cone beam. And then you can shoot 1 times and then get it to do the image reconstruction. But because we have only very small sensor, what I can do is I fix the small sensor, I fix the proton beam, and then I scan the object instead. Then we are able to use a small sensor to scan the big object. This is our idea to use what we have. Okay, we are poor. Then the first thing that we have to do is, get the signal from the proton to open our sensor. Because to shoot the proton beam to a sensor, it have to be a good timing. I mean, I have to open or trigger the sensor at the same time the proton coming in. This means I have to get the signal from the proton center as KCMH and read out the signal and then produce another signal and put into the sensor to open the sensor. And it was successful test by a single shift test. With this, we also playing by putting a pen in front of the sensor, putting a copper plate on top of the rotational state. We can able to verify that, okay, everything is synchronized. I open the beam, I rotate the sample, I detect the proton at the end. But of course, I don't have a good picture of the pen because it's scattering. And then we come to more complicated part. We put the 3 sensor in an array and put the proton from the top to the bottom. And then here we want to verify a tracker, the one part of the PCT. And then the proton coming in, shooting through this sensor, and then we get the information. This go inside a dark box to reduce the noise. And then we go back to more complicated one. We have 6 sensor. This is our last 6 sensor. I cannot break any one of this. And then, okay, we shoot the proton through, but here we also would like to test the calorimeter. How to have a calorimeter? The idea is the sampling calorimeter where we put the absorber material in front of the sensor here. Then this means that the proton deposits some energy inside the absorber, and then the number of proton reduced with the multi-layer of the sensor should tell you the energy of the remaining proton. But luckily we only have 6 layers here. I mean in the models of the backend they have like 41 layers of the sensor. But here we would like to proof of principle that what we have here. And then we shoot the proton passing through here. Well, the calorimeter can be another things. We also think about something else apart from the sensor. Then we think about the glass scintillator calorimeter. Some of our students do produce the glass at the glass lab in Nakhon Pathom, Rajapat Nakhon Pathom University. With this glass, there are some combination of the material science that when the proton hit, it should emit light, let's say. Then we really produce the glass ourselves, put inside this box. There is some light collimator, and then there is a light detection. And then we really found the light that coming out from this glass after we shooting proton in. This means we really can produce the glass scintillator ourselves here. And then I put in the water to be a phantom, and then we move the location of the glass here. Well, this one I told you this is the calorimeter. We have to put the sensor and then the absorber in the layers, or we can put all of them be a glass scintillator or any kind of scintillator. Well, come to our related parts. Because we have to move, then we have to do something automatically. I mean, we have to really put the Y inside the wall of the partial room and control room to control the proton beam from the control room, to move the phantom from the control room, to open the beam from the control room. And then I have a quick video, I think. Not available, so sad. Okay. Actually, I told you this is our 6 sensor that we have. The proton should come from this direction, and the phantom is here, and then our 6 sensor is here. Then, to control everything synchronizingly, this is the hard things that we also produce. We call it the trickle controller system. The trickle controller system control the proton beam through the TSS box of the proton therapy. This means we are able to control the proton on and off in our desired parameter that we input. Actually, this one take an advantage of at KCMH. There is a trigger additional system to measure the height of the body for the movement cancer. If you're breathing in and then the height of your body is higher, then it stop shooting proton, and then it lower it. They can again shoot a proton again. We took an advantage of this one and produced our own electronic device that can really turn on and turn off the proton beam in our desired time. And then this guy also connect to the rotational state and three-dimensional state motion, and also go to our sensor. And here we also test that, okay, we open the proton beam first, open the alpine, and then after that we are able to rotate the things in. Then another I would say another problem is because the proton that coming in, there are too many protons. Because if I remember correctly, it's 10 to the 9 proton per second or something. Maybe I'm wrong, but it's too many proton come to our sensor. This means we have to produce the collimator. We just make a collimator from the acrylic and then reduce the number of proton that we are able to measure the proton beam. But without the collimator, we have the beam look like this in our sensor. Then to do a track reconstruction, to get an image, we have to do a track reconstruction. We do a simulation from Jan 4 simulation, and then this is a 70 MeV, a bit spread beam, and then this is higher energy. And then we get the point from the simulation in order to track. And then one of our students calculate do a track reconstruction and calculate the efficiency of the track reconstruction. And then here, with the higher energy, you can track better than lower energy because this is more widespread. And then this is our result. Actually, this is super preliminary result. I mean, we have the beam of the proton that passing through the collimator. We have a 6 point here from the sensor that we have. He produced the algorithm to track the proton. And here is the proton that he can really track without any phantom, without any absorber. And this project is still going on and not finished yet. I would say this is kind of a progress of this project. We hopefully I would say we are able to develop the hardware in our desired level. I mean, we are happy with our hardware already. Now turn into the software part. We have to really develop the software, develop the algorithm to track the proton, and then use this information of the proton and also the proton energy to become the image reconstruction in the future. And I think this is all of my talk today. We love take picture. This is my team. Thanks. Thank you.
Very nice work. Thanks a lot. You showed the outline of the detector, and you have the trackers in front and on the back. But can we see the trackers on these photos?
Which photo? Sorry. You mean the first one, no?
Show the schema of this one.
This one, okay.
Yeah, you have this brown tracking chambers in front of the phantom and downstream of the phantom. And can I see the trackers on this photo?
No. We don't have only 6 sensors. I mean, okay, if I take this one, we use the same sensor. We have only 6 sensors. We don't have, we use the same sensor to test the tracker, right? I just test the tracker that we are really able to track the proton. And then I take the same sensor and turn it into the calorimeter and then test the calorimeter. Then I would say this one don't have the tracker yet because our limitation of the sensor.
Okay.
Yeah.
So my question just relate to the resolutions that you expect to get from your system. compared to the one at backend or compared to the CT scan?
Well, to be honest, we are not reached that state, but we just follow some publication. There are many publications talk about the image reconstruction of the proton CT, or most, I would say most of them saying that the resolution is better than the mono CT. Actually, this graph show the dual energy CT, X-ray CT scan, and single energy CT scan. You can see the uncertainty. Actually, the relative residual error on the y-axis is higher than the proton CT. There's some calculation that okay, the uncertainty is lower than the X-ray CT. But we are not reached that state yet. Our postdoc doing that now.
May I have another question? So you said that now you use like only a single sensor, or maybe just only a few sensor. Do you have plan that maybe in the future, if you have more money and you can get more sensor, to have a kind of array sensor to have faster scan?
I think Ajahn have a plan.
So we collaborate with Alice and we learn some sensor technology from CERN. At the end, if we have enough support and enough people, we would like to develop this sensor here in Thailand. And we have one PhD from Indonesia, Abdul. Can you show you? Get up, yes. He will be one of the main guy of our SUT that finally, it doesn't matter who said, CERN got this, PSI got that. And the question is, what Thailand has? So if we have enough support, I have to say that the software to design the sensor, it costs about 8,000 baht per year. Okay, it's not cheap. And once you get the sensor design, you have to send it to the foundry, and to get one bunch, you have to do 3 to 5 million baht per bunch. This one doesn't count about the wafer and circuit, everything. So at the end, if you want to do something, I would have said that if you want to do deep technology or high technology, you need high investment and high talent. Okay? Not just your dream, no? We want to do digital 4.0, but we have 0.1 budget. Okay, sorry about that.
But it's true. Thank you.
Yeah, but we have to prove to them that we can do something first, because before we can ask for more budget. Okay? Sorry. Thank you.
I have a question about the range of protons. Because now you have a phantom of how many centimeter thickness?
This one is 5 centimeter only.
So how about if we want to, what is the target organ that you will have a proton?
We just use acrylic now. This is the easiest one that we can produce. Then,
but I mean, if you want to do for the real organ, the range of 250 MeV protons is only 38 centimeter. Then it will stop inside the phantom, actually.
You need.
So we can't do PT tomography by this energy. Do we have any plan, or do we have any suggestion on this? Because otherwise the proton will stop already. We can't detect any proton that transmitted to the detector.
So this part I have to answer then. I'm sorry. Anyway, I have to stay in your scene, no? You don't? So actually, what we try to do first now, we have another team called radiobiology team, led by Dr. Dr. which is postdoc of mine, and another postgraduate researcher, Prawa. We have to do the, we call in vitro experiment. We want to try to do some the cancer cell line, we culture it, and we put it on the well plate. We want to try to see that our proton can distinguish between cancer cell and normal cell or not by using the standard phantom. You mean the cap fan one or whatever? That's our plan because the well plate is not so thick. The well plate, the phantom for the biological sample. So that's the first way that we want to do it. And after that, we plan to do the in vivo animal model, like mouse that Martin showed. But this one, I will lock it, okay? I don't let them run around. And finally, as you mentioned, and I also would like to sell more research at SUT, is that we also aim at GBM, glioblastoma, multiforme, whatever, or recurrent one. This one is not so thick compared to the torso body. And at SUT, in about 6 or to 10 years from now, we also going to do another technology we call the BNCT, boron neutron capture therapy, which is a binary radiation system. So I would have said that from now on to the 10 years, Thailand will be in the exciting time of the particle therapy. We will have proton, we will have neutron, and of course at Chiang Mai, Professor Sakon also mentioned about flash, and we would like to do that. We have dream, but we have to go there.
So in the real life, we have the body which is thicker than 38 centimeter. What is the solution? That's the question.
Actually, this one, if you have 250 MeV, it can penetrate your trunk.
Yeah.
Then you have to boost the proton. Actually, one have to think, I don't know, I think PSI also have this project before. I think they have the project to have the booster, no? Booster that higher energy than 220 MeV. At that case, you can have enough energy.
We did proton radiography, so it's not a CT, but just like a normal X-ray. And at that time, we did not have our superconducting cyclotron, but we were using parasitically the 590 MeV cyclotron of PSI. And that allowed us to shoot through not patient, but we did some animal images with that. But that's long ago. This was in 95. And then we decided not to follow up on this. But it's, of course, a very valid approach. And you measure directly the proton range. So this is why this is so interesting.
So in short, you do two things. First, increase the energy of proton. And the second one, just take the organ out. Just like you did for the patient eyes. You just cut it open and take it out.
So you need the bigger cyclotron and then. But another question concerning about proton, which produce neutrons as well. Do you have to take it to account for neutron production when you shoot proton into the body?
Actually, yes, because in our calorimeter consists of the absorber. There are many candidates of the absorber, for example, copper, aluminum foil, or carbon fiber. You have to think about which one that produce the secondary radiation less. Yeah. Now we didn't care about the radiation yet because we have very few materials. We do check with the survey meter, but it's safe for us for sure. But in the future, yes, of course, we have to think about that.
Okay, sorry, I have to cut it short now because the next speaker is waiting. I'm sorry. That takes too much time. Thank you, Dr.ณรงค์